This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, let's get back to the subject at hand, which is classical mechanics. No, classical field theory. But classical field theory, as I've emphasized several times, is a special case of the general rules of classical mechanics. And that's the way it should be thought of. As an example, maybe the prime example of the basic rules of classical mechanics. So I think we have to review just a little bit about classical mechanics and then apply it in the field theory context. What I particularly want to get to tonight is the connection between symmetries and conservation laws. Now, we've done that in the context of classical mechanics, but it's especially interesting and really takes sort of front seat in the subject of relativistic field theory, the connections between symmetries and conservation laws. So let's go back a few steps and review a little bit about classical mechanics, least action, Lagrangian, and conservation laws in the simple context. I don't think we'll have to do, come in. I don't think we'll have to get too involved with Hamiltonian mechanics tonight, although later on we'll want to. But let's just review very quickly the mechanics of a system of particles. And for our purposes right now, we could have just one particle moving in one dimension, although everything I say could be generalized just by putting a little index I next to some symbols. I'll probably do that. All right, so we have a particle with a coordinate x. Incidentally, sometimes I use q for coordinates, sometimes I use x. I'll try to be clearer about the logic if I change symbols. Ask me about it if it confuses you, but I think probably it won't too much. Anyway, particle is described by a coordinate x, which depends on time. Of course, there could be n particles, and they could have three-dimensional positions, in which case we would just put a little I downstairs to indicate which coordinate we were talking about. And the object of a problem of mechanics is to compute the orbit. Vertically, as always, we put time. Horizontally, we put x. However many x coordinates we need, but I'll just draw one. And then the particle moves through space-time along some orbit according to the principle of least action. And the principle of least action says minimize, or at least make stationary. I'll describe what I mean by stationary in a minute. For our purposes, it can mean minimize. Minimize the action, and the action is the integral of the Lagrangian, which depends on the coordinates and the velocities. X dot stands for dx dt, integrated with respect to time. And just to remind you, we hold the endpoints fixed and require that this quantity is minimized. Minimized with respect to what? Whenever you say something's minimized, you imagine that you can explore some space of possibilities, and then minimizing means find the possibility which gives you the minimum value of the action in this case. So we're talking about exploring different trajectories, but in particular, let's make a little change in the trajectory. Some small change in the trajectory. The small change in the trajectory could involve a change from beginning to end, or it could just involve some small little region here where the trajectory is changed. And recalculate the action. Recalculate the action as it deviates from its value along the true trajectory, and then require that, that when we vary the trajectory a little bit, that the action always increases. Now, assuming that it increases really is basically the same as assuming that it doesn't change. Let me just remind you, when you're minimizing a quantity, for example, supposing you're minimizing something with respect to one variable, only one variable now. In this context, we're minimizing with respect to an infinite number of variables. The infinite number of variables are all the positions along the entire trajectory. So it's a very complicated problem of minimization where we're minimizing with respect to an infinite number of variables. But nevertheless, let's examine the problem of minimizing something with respect to one variable first. All right, so the same a quantity, in this case, let's call a quantity f, and it could be f of some variable x, and it's minimized at that point over here. So as you well know, the rule for finding a minimum is just to differentiate x and set it equal to 0. Another way to say the same thing is to require that at this point here, that if we make a little shift of x, then that the change in f, the change of f, delta f, when we change x a little bit, should be 0. That's the statement, that's the same as the statement that the derivative is 0, that the change is equal to 0. Okay? In both directions, no matter which way you move. If that's the case, that the change is 0, 0, of course, means only for very, very small excursions. Right? So the first order change should be equal to 0. That's the same as saying df by dx is equal to 0. We could also say that the change in f when you move x a little bit is the derivative of f with respect to x times delta x. If df by dx is equal to 0, so is delta f. All right, so you get the idea. Now, supposing you have many variables. In particular, let's suppose we have 2 variables. So there's another variable sticking out of the blackboard here. And again, we have some function which now depends on 2 variables, let's say x and y. And we're looking for some hole, some dip in the function where it achieves its minimum with respect to both variations in both directions. In fact, we're looking for a place where no matter what direction we move off in, the function doesn't change to first order. That's, the word for that is finding the stationary points of the function. But a particular example is finding the minimum of a function. If we found the minimum of a function with respect to all variations of this point, then what we want is that the derivative, that all the derivatives of f with respect to x equals 0, with respect to y equals 0, or a shorthand version for it is that if we're right at that point and we vary both x and y, or all of the variables, whatever the variables are, that the change in f, again, should vanish. That's a shorthand version for saying that all the derivatives are equal to 0. So in the same manner, if we're looking for the minimum of the action, what we want to do is we want to explore nearby trajectories. We think we have a solution. This is supposed to be a solution. We think we have a solution. We want to explore nearby trajectories and require that the change in the action is 0 when we make a small change in trajectory. Let's just write that the variation of L of x and x dot dt is equal to 0 when we change the trajectory a little bit. Now, what does changing the trajectory a little bit mean? It means we add to f to x of t, we add a small change. X of t was supposed to be the original solution. Let's add something small, let's call it epsilon, times an arbitrary function of t. What are the variables in this problem that we're minimizing with respect to? We're minimizing with respect to all these variables f of t1, f of t2, in fact, f all along here. This little bump here represents f. Right? So the question then is, how does the action change when we change x a little bit? All right, that's easy to work out. Oh, incidentally, yeah, let's write this out. the change in x is just equal to epsilon times f of t. And of course, it also follows that the change in the velocity is epsilon times f dot of t. We just differentiate with respect to time both sides of the equation. If x changes by a little bit, then the velocity associated with x changes a little bit. And we can imagine we have any number of coordinates and do the same thing. It's not restricted to just one coordinate, but let's fix on x and see what this equation says. All right, so this is easy to work out. We just write that this is that the change in the action is equal to the change in the Lagrangian integrated with respect to time. But what's the change in the Lagrangian if we change x and x dot a little bit? Well, that's easy. That's the derivative of the Lagrangian with respect to x times delta x. But delta x is just proportional to f of t. We can put an epsilon on the outside here. The change of x is just f of t. So let's put f of t there. Epsilon times f of t, but I left the epsilon outside. And then the Lagrangian also depends on the velocity. So we add plus the derivative of the Lagrangian with respect to the velocity times the change in the velocity. Integral dt. That's the change in the action when we change the trajectory a little bit by an amount. Delta of x dot, sorry, is just epsilon f dot. F dot. Epsilon is already outside here. Any question about this formula thus far? It's just a simple formula that the change in the action is gotten by varying the Lagrangian a little bit, by varying x, and by varying x dot. Now, what's the next step? Anybody remember? Integration by parts. This over here, the f dot. And what we're using is that if you have a integral of the form of the product of two functions, a times b dot, that's equal to minus the integral of a dot times b, as long as you don't vary the endpoints. As long as things are frozen at the endpoints, then there's no contribution from the boundary in the integration by parts. And so it's very easy. Wherever you see a time derivative, you have a product and an integral. This, of course, is dt. If you have a product and an integral of something times a time derivative of something else, you can switch which one of them carries the time derivative, but you'll have to change the sign. All right, so that's the rule of integration by parts. And that's what we have over here. We have a time derivative f dot over here times dl by dx dot. So all we have to do then, we can do, not all we have to do, but what we can do is change the sign, put the time derivative on the other factor, and get rid of the time derivative here. Now, why was that a nice thing to do? It was a nice thing to do because it isolates f by itself without a time derivative in both terms. So that means we can factor out of the bracket, not out of the integral, but out of the square bracket here, we can factor f. Both terms are proportional to f, and we have f dt, f of t dt. Now, what do we want to be true? We want this to be true, that this is equal to 0 for every possible variation f of t. We want to explore all neighboring trajectories, all possible neighboring trajectories, and require that every possible shift in the trajectory, in other words, every possible f, gives the same answer when you vary the action to first order, namely 0. All right? So that means that this has to be 0 for all functions f of t, all possible functions. Well, if you think about it a little while, you realize the only way an integral like this can be 0 for all possible f of t is for the thing that it multiplies to be 0. Supposing the thing that it multiplied here was not equal to 0 somewheres. at some time. Supposing the thing that was here was not equal to 0 at some time, then we could choose a function of time that was the f of t that was narrowly concentrated near the place where we knew the thing in the brackets was not equal to 0, concentrated only in that region, and we would get something not equal to 0. F not equal to 0, this thing not equal to 0, over a small enough range, we'll get something not equal to 0. So the only way that an integral like this can be 0 for every possible f of t is for the integrand here to be 0, for the thing in the bracket to be 0. This is analogous to testing the function in all possible directions. All possible directions, all possible variations, if you require that f be stationary with respect to all possible variations, it tells you that all of the derivatives equal to 0. The analog here is that what's in here, in the bracket, must be 0 for all times between here and here. That's the Euler-Lagrange equations. That's the derivation of the Euler-Lagrange equations. Let's write them down. d by dt of the derivative of the Lagrangian with respect to x dot minus the Lagrangian with respect to x. Let's use the same symbol here. All right. Now, the only difference, if we have lots of coordinates, and now let's call the coordinates q instead of x. They might not be the Cartesian coordinates of a particle. They might include angles, points along some arbitrary curve, some more generalized kind of coordinates. Exactly the same thing will be true, except we'll just call the q's, and we'll call the x's q's. It's just a renaming. But if there are many, many coordinates, well, many or more than one, then we'll want to put an I there. And so for each coordinate, x, y, z, different particles, there will be an Euler-Lagrange equation, which is essentially of the form of Newton's equations for each component of the configuration space. So we've been through that. I assume that you have that in your notes. That's the derivation of Euler-Lagrange. And it's the basic equation of Lagrangian mechanics. Now we want to generalize that to field theory. Field theory is a special case of this, where the various coordinates correspond to the values of fields at different positions of space. We worked out an example, which was the string, by subdividing space into a lot of little segments, or a lot of little positions, and then instead of thinking of a continuous field, we thought of the value of a field at each point. We discretized it. We discretized the field and replaced it by a rather dense collection of degrees of freedom. We called the degrees of freedom, we didn't call them x, because x now labels doesn't label a location of a particle. It labels a location in space. In other words, it labels the position that we might be evaluating the field. The field becomes the coordinate. The field becomes the degree of freedom. In other words, the q's in this problem are the fields at the different positions. We could call it phi of I, meaning phi at the position, at the ith position. Or we could call it phi at point xi. Or we can just call it phi of x. Phi of x sort of has the implication that we're going to a limit where we take the points to be so dense that this field becomes a continuous field. And we can imagine doing that process. And if we do imagine it, then the field theory just is a special case of classical mechanics where the q's are just the values of the fields at the different points. Now, I emphasize, they are not locations of anything in space. They are the values of fields at different points in space. But, as we discussed last time, you can summarize all of this passing from a discrete description to a continuous description, replacing sums by integrals, differences by derivatives. We can summarize all of this by saying we have a Lagrangian which begins as a sum over position, sum of all the kinetic energies, sum of all the potential energies, and becomes replaced by an integral dx. Now, as I said, x now does not stand, the Lagrangian is an integral dx. The integral over x replaces the sum over I, integral dx, of some Lagrange density. Lagrange density means you integrate it over space to find the Lagrangian. And what does the Lagrange density depend on? In general, the Lagrange density will depend on the values of the fields at each position. It will depend on phi of x. It may also depend on differences of phi at neighboring points. Yeah.
Is there some meaning between switching from uppercase to lowercase?
Oh, of which? The L? Of which? Of phi? No, none whatever. Have I switched? Oh, you consider this uppercase?
Yeah.
Oh, no, uppercase I will, if I do use uppercase, I will do this.
Oh.
Yeah. No, that's just sloppy, no, none whatever. Good. Right, so phi of x, right, so the sum over the degrees of freedom becomes an integral over x of a thing which is called the Lagrange density. And in general, the Lagrange density will depend on phi. It will depend on time derivatives of phi, just like Lagrangians depend on q's and q dots. Lagrangian will depend on phi. It will depend on phi dot, which means the time derivative with respect to time, with respect to t, the derivative with respect to t. And let me write that just as dt phi, that shorthand for d phi by dt. Here's some notational equivalences. Phi dot equals d phi by dt equals dt phi equals phi sub t. All the same thing.
Isn't phi dot really d dt?
Phi dt.
Well, it's not the partial, it's the total.
No, it's the partial. That's what I mean by phi dot.
What if it were omega dot? Wouldn't it be
What's
the total
omega?
derivative?
What's omega?
Angular momentum, or I mean, you know, in general.
Well, if a thing depends on more than one variable, and phi depends on more than one variable, then it has a collection of derivatives with respect to each variable.
But I'm just saying, usually isn't the dot always the total derivative?
If you like, if you want me to use for dot total derivative, no, I don't use it that way, and I don't think it's commonly used that way. But let's, okay,
like
let's not use
if you see h dot equals the Poisson bracket or something like that.
Yeah, let's not use, fine. In fact, modern physicists don't use it that way. They use it quite often to mean derivative with respect to t, keeping everything else fixed. Yeah. In fact, it's so easy to write it that I think I want to keep it around as a notation. That's definition now. Definition of phi dot, derivative with respect to t. And if I ever have a situation where I want to think about the total derivative of something, the total derivative may mean along some orbit or something, then I will just write d phi by dt. I will write d phi dt. Since I will so rarely have to use this, I prefer to save more complicated notation for something I use rarely. Okay, these are all the same thing, and I let's put phi sub t here, meaning to say the derivative of phi with respect to t, keeping everything else fixed. But what else can L depend on? L can also depend on differences of phi between neighboring points. Right? So you could have in the Lagrangian phi appearing at each point separately, but you could also have the derivatives of phi appearing in the expression for the Lagrangian. And in the Lagrangian we wrote down the potential energy did involve differences of phi at two different points. That translated into something involving derivatives of phi with respect to spatial positions. Right? So we could have equals dx phi equals phi x. We can also have d phi by dy and so forth. So what can appear here is derivatives of phi with respect to t, derivatives of phi with respect to x, and derivatives of phi with respect to y, and derivatives of phi with respect to z. All of them can appear in the Lagrangian. Notice it's kind of symmetric between t's, x, y's, and z's. I don't just call this derivatives of phi with respect to the coordinates. I can also call these derivatives phi sub mu, where mu runs from 0 to 4, t being x0, x being x1, y being x2, and z being x3, in a sort of relativistic notation. All these things mean the same thing.
You want to change the dx and have the dx for
Where? Yeah, I was just about to change that. Here. Yeah, exactly. That's right. But the integral dx, when I was thinking about a string, there was only one space coordinate. When I'm thinking about a field in 3 dimensions, then I want to put d3x. All right, now first of all, what is kinetic energy and what is potential energy? In the example we worked out here, the Lagrangian had, for example, phi dot squared in it. That was simply the kinetic energy of every point oscillating up and down. When we thought about it as a string, phi dot squared was the kinetic energy. So typically, in a Lagrangian like this, there will be a term 1/2 phi dot squared. That's kinetic energy. It depends, and kinetic energy by definition means the things which are quadratic in the velocities. And velocity means derivative with respect to time. All right? So a typical Lagrangian might have 1/2 phi dot squared. And then in the example we worked out over there, there was a minus c squared. Why was there a minus sign here? Anybody remember? In the potential energy? Because the Lagrangian is kinetic energy minus potential energy. All right? And what was the potential energy? The potential energy depended on the difference of the field at neighboring positions. And so there was d phi by dx squared. And of course, in a more general context, we might also have minus c squared d phi by dy squared minus c squared d phi by d z squared. It's good to write it explicitly just to keep track and to remember that this term is kinetic energy, and this stuff here is potential energy. It doesn't depend on velocities, doesn't depend on the motion. It does depend on the configuration, how the phis are their dependence on space, but not on time. So this term here is the kinetic energy. This is potential energy. There could be other terms in here. There could be things which depend on phi itself without derivatives. It's a perfectly rational thing to put into a Lagrangian. For example, each one of these particles could have an energy which depends on its height. Not on the difference between neighboring heights, But there could be a term in the energy which would just depend on the height of each particle. For example, if the whole thing was in a gravitational field, okay, then we might put into here something which depends on phi. Not d phi by dx, not d phi by dt, but possibly just phi itself. So there might also be dependence on phi. Let's put some dependence on phi in here. A nice simple example would be minus some constant, I'll call it mu, and I'll put a 2 there for purely conventional reasons, times phi squared. And I choose phi squared for no specific reason except that it makes an easy equation when we work out the equation of motion. It could be phi cubed, it could be phi by itself, it could be cosine of phi, but something which depends on phi and not its derivatives. So this would be a term in the potential energy which would depend on the coordinate of each one of these separately, not on the differences between them, whereas the potential energy could also have a dependence on the gradient of phi, the gradient in space. All right, this is the Lagrange density here. The Lagrangian is the integral of that, but the action is the integral of the Lagrangian with respect to time. So that's yet one more integral. The action is the integral of this dt, which means d4x. That's the structure, that's the general structure of field theory, not that specific Lagrangian, but a Lagrange density integrated over space and time is the starting point of most discussions of field theory. We'll start with Lagrangian. Now, what is the condition that the theory be Lorentz invariant? The condition that the theory be Lorentz invariant is very, very simple. You, of course, first must start with some idea of what kind of transformation properties your field variables have. The field variables could be scalars, they could be vectors, 4 vectors. You have to give them a transformation property under Lorentz transformations, not just under rotations of space. So the field variables could be any particular kind of, as I said, scalars, vectors, tensors, which we haven't spoken about yet. But in this simple case, I'm imagining the field variable is a scalar. We'll go on to more complicated cases with vectors, but for the moment, just scalars. The field variable phi is a scalar. The important thing is that the Lagrange density be a scalar. If the Lagrange density is a scalar, it means the action doesn't depend on which Lorentz frame you use. So if the Lagrange density script L here is a scalar, you don't have to even think about whether the equations are Lorentz invariant. They will be. All right, now this is a Lorentz, as I've written it here, this is a Lorentz scalar. It has the form phi dot squared minus c squared. Let's set c equal to 1 for simplicity. At least at this stage, let's set c equal to 1. The thing in the Lagrangian is d mu phi. Remember what this means. This stands for the 4 derivatives, time derivative and the 3 space derivatives, these things here. These stand for the same derivatives except with a change of sign of the time component. All right? So d mu phi stands for the complex of objects phi t, phi x, up to phi z. And d super mu phi stands for the same thing except the time component changing. Then when I multiply the contravariant derivative times the covariant derivative, it gives me something with a time derivative squared having the opposite sign from the space derivatives. In fact, I think I want to put a minus sign in here. And a 2. So the Lagrange density that I've written down over here is nothing but the scalar which is made by contracting together the covariant components of the gradient of phi with the contravariant components. That makes a scalar. And as a scalar, It tells us the action is invariant, and if the action is invariant, the equations of motion will be invariant. So it's real easy to design relativistically invariant theories.
It doesn't include the d squared term.
What's that?
It doesn't include the last term.
Oh, this one here? Well, in fact, it does. Since phi is a scalar, so is phi squared.
That's what you wrote down.
Oh, sorry. Yes, you're right. Minus mu over 2 phi squared.
Is that mu over 4, or is that 2 supposed to be like outside?
Thank you. Of course, it doesn't matter. It's a definition of mu, but I did intend that, that the mu also had a factor of 2. Right. Right. Good. Okay. So that's the basic setup. Now, the next question is, given a Lagrangian like this, what are the Euler-Lagrange, what are the analogs of the Euler-Lagrange equations? In other words, what are the field equations as partial differential equations? For the case of a coordinate which only depends on one variable, namely time, the Euler-Lagrange equations were just ordinary differential equations for the time dependence. Now we have a problem which is to figure out not only the dependence of phi on time, but also on space and time. And so the equations are going to be partial differential equations, or wave equations to be specific. So the question is, how do you take a thing like this and minimize it? Let's just take this to be a special case. Here's the general form. L is equal to an integral d cubed x of this kind of thing here. The action, let's write the action is the integral d4x. Well, you do exactly the same thing as in the simpler case. You say, let's suppose that phi of x and t, which I could just write as phi of x mu, but phi of x and t, let's suppose that's a solution. And now let's add plus epsilon times a function of x and t to it. What we require is that when we change the field in this manner, that the change in the action is equal to 0. That's the analog of saying that the action is stationary. In fact, it's not the analog, it's a statement that the action is stationary when you change the orbit of the field. Think of this as sort of the orbit. How the field varies in space and time is the generalization of the orbit of a mechanical system. And we're requiring that the action be stationary. Well, let's work it out. This is not so hard to do. If delta phi is equal to epsilon times f of x and t, then what is the change in, let's call it phi mu? What's the change, if there's a change in phi, what is the change in the derivative of phi with respect to x? Very simple. It's just equal to epsilon times the derivative of f with respect to x mu. So, for example, this stands for the complex of equations, I don't have to write them out, that the change in the time derivative of phi is epsilon times the time derivative of f, and likewise for the other components, f of x and t. If you change phi by a little bit, then the change in the derivatives is just the derivatives of the change in phi. Okay, so now let's calculate the change in the action. The change in the action is going to be the integral d4x times the change in the Lagrangian when I change the field a little bit. And what is that? That's the derivative of the Lagrangian density with respect to phi times delta phi, that's epsilon on the outside, f of x and t, plus the derivative of the Lagrangian with respect to phi mu, phi t, phi x, phi y, phi z, times the change in phi mu, which is the f by dx mu. I think I have that right. And of course, this stands for a sum. This stands for a sum over x, y, and z, or x, y, z, and t, all of them. That's it. That's the change in the action. What do I want to do? I want to set this equal to 0. That's the condition that the action be stationary. Now, over here I have f of x and t. Here I have the derivatives of f. What do I do to go from to get rid of this derivative on f here? Integrate by parts. The rule for integrating by parts, I'm not going to work it out for you, but the rule for multiple dimensional integrals is exactly the same as the rule for single integrals. You're allowed to take the derivative off here and put it on here at the expense of a sign change. So this is the same thing as minus, and now the derivative with respect to x goes here. Let me write it out. Let me write it out a little more clearly. Minus d by dx mu of the derivative of the Lagrange density with respect to phi mu times f of x and t again. All right, now we're getting close to being in business. We have f multiplying both factors here, so I can put a bracket around here and factor out the f. The next step is exactly the same as it was in the particle case. This is supposed to be equal to 0 for all possible functions of x, for all possible ways of changing the field away from the solution. In other words, we're exploring all variations of the field away from the solution and requiring that the action is stationary. This has to be 0 for all f. How is that possible? It is only possible if the thing in the bracket here is 0. So we come to the conclusion that for each field in the problem, we're dealing now with a problem with only one field, phi. If there were several fields, we would have a separate equation for each one. But let's deal with the case of one field. Our equation of motion, our Euler-Lagrange equation of motion, which follows from the Lagrangian, is here it is. Take the derivative of the Lagrangian with respect to phi mu, differentiate it with respect to x mu. This is in close analogy with the derivative of the ordinary Lagrangian with respect to q dot d by dt. Right? Close analogy, but there are 4 terms in here. Derivative with respect to t, with respect to x, with respect to y, with respect to z. And then subtract off minus the derivative of L with respect to phi equals 0. All right, so now we have a kind of machine. You feed into it a scalar Lagrange density. And I think from now on, I'm simply going to call L, script L, the Lagrangian. It's properly called the Lagrange density, but it's a mouthful. For a field theory, we'll just call it the Lagrangian. Maybe I won't. Maybe I'll continue to call it the Lagrange density. But if I slip and call it the Lagrangian, either correct me or, well, it doesn't. If it's clear, don't bother. All right, so this is our equation of motion. And now let's work it out. This is our equation of motion for a field phi. Let's work it out for our favorite Lagrangian over here. Here's a specific Lagrangian. Let's work it out. This here is a sum. Okay? So let's start. What does it say? It says, the only thing we have to remember is that the time components get the opposite sign from the space components. That's the main thing here. All right, so this says that d by dt of partial of L with respect to phi dot, that's the first term, I guess, minus d by dx partial of L with respect to phi x, and likewise for y and z, minus the derivative with respect to phi equals 0. And let's work it out now. What's the derivative of this Lagrangian with respect to phi dot? Just phi dot. 1/2 gets eaten up by the 2 here. The derivative of the thing inside the bracket with respect to phi dot is just phi dot. Okay? So our first term here becomes dl by d phi dot is just replaced by phi dot. And what's d by dt of phi dot? Phi double dot. 2 time derivatives. Second time derivative with respect to t. Or just phi tt. We could call it phi tt. Second time derivative of phi with respect to t. Now, what about the derivative of the Lagrangian? I made a mistake. This should be a plus. This is a plus sign here. The minus is here. No, there's no minus over here. This should not be minus. This is plus. All right, what's partial of L with respect to phi x? It's minus c squared times phi x. All right, so let's put that one in. Minus c squared phi x. What's the derivative of phi x with respect to x? Phi xx. 2 derivatives. I'll write it out in longhand in a moment, but let's... And likewise for y and z. So there's minus c squared phi yy minus c squared phi zz. And now let's include this last term just for fun. I'm going to drop it soon because it'll come back, but for most of tonight I'll get rid of this. Minus mu phi squared. So we have to subtract the derivative of, where is our equation? We have to subtract minus the derivative of L with respect to phi. And I think that gives us, a plus mu phi.
Plus 2.
Right?
Equals 0. I guess equals 0.
Is equal to 0. No, there isn't a half, because each one of these things was squared. So when you differentiate it, that's why the half is there. The half is there to avoid the half in the equation of motion. Right. That's, all right, so let me write this out in longhand. In longhand, it's second derivative of phi with respect to t squared minus c squared second of phi with respect to x squared plus second of phi with respect to y squared plus second of phi with respect to z squared all equals, sorry, let's put the plus mu phi equals 0. Okay. I only kept the mu phi there just to illustrate in some generality what it would mean to have a term in the Lagrangian or a piece of the Lagrangian which depends explicitly on phi. I'm going to drop it now. We're going to come back to it. Is it a minus sign? I think it's a plus sign. I think it's a plus sign, yeah. Right. Okay. Incidentally, the mu phi squared term is called the mass term, and it has a great deal to do with the mass of the quanta of the field. In fact, it is nothing but the square of the mass of a particle that might be described by this field. Remember, there's a connection between fields and particles through quantum mechanics. So the electromagnetic field, the particles that it describes are photons. Photons have no mass, so you would not have this term for photons. Other particles which have mass, you would have this term. But we're going to come to that. Why do I say it's a mass? Well, it's not in the least bit obvious at the moment. But let's just drop it and study the theory without that term. Here is the equation describing, it describes light. It describes the propagation of any massless field. Sorry, it describes any field which propagates with the speed of light. Let's just look at it in one dimension. We've, of course, already done this. For example, supposing the field only depends on time. Of course, it depends on time. If it's any kind of decent field, it's going to depend on time. But supposing it doesn't depend on all three coordinates. Suppose it only depends on x and not y and z. How can that be? Well, if a wave was moving down the x-axis, a plane wave with no variation, perfectly uniform wave fronts, moving down the x-axis, then it would have no dependence on the other two directions. As a uniform, infinite plane wave moving down the axis like this would have no dependence on y and z. And so for that situation, the wave equation would be d second phi by dt squared minus c squared d second phi by dx squared is equal to 0. All right. There are, in fact, two kinds of solutions of this equation. This is the standard wave equation of a field which propagates with a uniform velocity, c. And the solutions of these equations are functions, two kinds, two of them, any function of x minus ct or a function of x plus ct. Doesn't have to be the same function. Take any function. Let's call it f. Let's not call it phi. Let's write phi is equal to any function of x minus ct. In fact, you can add plus another function of x plus ct. What does this term describe? Right. You start at t equals 0 with any old function of x. And now, when you write function of x minus ct, it just describes exactly that same profile moving with velocity c down the x-axis. What about this one? That just describes the profile g moving in the opposite direction in the left direction. Now, of course, there was nothing sacred about a wave moving along the x-axis. I could have rotated it and have it moved along any axis, or even any catty-cornered axis. But this is the typical kind of solutions of these wave equations.
The wave shape is maintained?
The wave shape is maintained. That's right. That would not be the case if we added in the mu. Was it plus or minus? I think it was minus, plus or minus, mu phi. In other words, with this extra term over here. It would not be the case then. So this is a special feature of what is called the massless wave equation. It's called the massless wave equation. It corresponds to the fact that this describes waves that move with a particular fixed velocity. And so the whole thing just moves off with a uniform velocity, same way a light ray would, light beam would. Yeah, question?
But if g of x is not this,
If
if you have the two of them, then they're different shapes moving, so it doesn't look like a...
Oh, yeah, no, right. Yeah, you could have, sure, you could have a shape like this moving to the right and add on to it a shape which looks like this moving to the left. And of course, when they pass through each other, you're going to see something much more complicated. But all they're really doing is passing through each other without doing anything very interesting. All right, so that's the general pattern. Left-moving waves and right-moving waves.
Phi is not a sufficient initial condition. What's the...
Say it again?
Phi itself is not a sufficient initial condition.
That's right.
What's the other part of the initial...
Time derivative of phi. Yeah. For example, here's the point. Another way to say it is this. Supposing I just gave you the field phi at time 0. Here it would be f of x plus g of x. How do I know that some piece of it is right moving? How do I know how to divide this up into, this is just, the sum of these two is just some function. How do I know how to divide it up into left moving parts and right moving parts? Well, if I also tell you what the time derivative is, then knowing both the function and the time derivative allows you to break it up into the two parts like that. And that's a little exercise you can do. So yes, you need to know phi and phi dot. Same exact story as with particles or with ordinary coordinates. You need to know the coordinates and the time derivatives to get started. Right? In any case, for the simple wave equation without mass term, this is what you get. Now, notice this equation, either with or without the mass term, the equation is linear. Linear means only first powers of phi appear. Higher derivatives of phi appear, but nothing ever involving products of phi or derivatives of phi times phi or derivatives of phi with other derivatives of phi. Linear equation means that the only thing that appears in it are first powers of phi, derivative of phi, second derivative of phi, and so forth. Under those circumstances, you can add solutions. If you have two solutions of the equation, you can add them together, and there's still a solution. You can also multiply the solutions by a number, and it's still a solution. So a linear equation, you can add solutions. Here I've just done it. You can multiply solutions by numbers, and there's still solutions. This equation is linear even with the mass term. What is it, from the point of view of the Lagrangian, that made the equation linear? The Lagrangian is quadratic. It involves phi squared, derivatives of phi squared, squares of derivatives of phi, and so forth. So it only involves things to the second power. That means when you differentiate the Lagrangian with respect to its various arguments, you'll only get first powers of phi. And so if the Lagrangian is quadratic, the equation of motion is linear. Do you know a mechanics problem that has a linear equation of motion? Mechanics meaning to say not field theory, but just particle motion?
Harmonic oscillator, I guess. Harmonic oscillator?
Yeah. Well, for even simpler, it would just be a free particle. X dot squared. Okay. That equation of motion is just x double dot equals 0, and that's very linear. Well, it can't be very linear. You're either linear or you're not linear. But if you want to have a more interesting example involving some potential energy, then for the potential energy in Lagrangian minus some constant times x squared. So it's the quadratic character of the Lagrangian, which in turn means the quadratic character of the potential and kinetic energy, which make the equation linear. Just to remind you, the equation of a harmonic oscillator is x double dot equals minus kx. Again, only first powers. And linear equations are particularly simple to study. Okay, that's
The mass part attenuates the wave always.
Is it what?
The mass part attenuates the wave.
No, well, it doesn't attenuate the wave. What it does is it causes, all right, I'll tell you what it does. It causes different wavelengths. You can think of any wave as being made up of different wavelengths. All right. It causes different wavelengths to propagate with different velocities. Dispersion. The result is it causes the shape of the wave to change. So the shape of the wave changes with time. It doesn't disperse away. It doesn't fade away, but it does cause the shape to change, and it'll wobble and do things, and more complicated kind of motion. All right. We'll solve these equations. But what I wanted to do tonight really was not to solve equations of motion, but to study conservation laws. An awful lot of field theory, quantum field theory, elementary particle physics, the whole works is the study of symmetries and the associated conservation laws. So let's take a 5-minute break and then come back and immerse ourselves in the theory of symmetries and the associated conservation laws. Two cases of the connections between. Now, they're really not two cases, but I just want to, for simplicity, separate them now. One of them has to do with energy conservation and the other, all other conservation laws. Energy conservation is a little bit special, although it can be cast in the same form as the others. What symmetry does it have to do with? Excuse me. Translation of the action with respect to time. In other words, if there's no special origin of time in your problem, for example, how could you have a problem in which there was not time translation invariance, incidentally? Yeah, for example, the universe is expanding. One time is not like another time. So that would be an example. Some problem with, for some bizarre reason, the force law was changing with time. So you can certainly imagine problems where you don't have time translation invariance, but most problems in physics have time translation invariance, which means it doesn't matter at what time you start. If you start the same way at one time or another time, the ensuing histories will be the same, except just lagging one behind the other by the time shift. When that happens, you have energy conservation, and I'm not going to go back through the derivation of that. That we did in the mechanics class, and it's a little more intricate than the other ones, so I'll just ask you to go back and recall the argument about how time translation invariance leads to energy conservation. But the energy conservation statement itself is very simple. If the Lagrangian, let's simplify the story to simple Lagrangians. We may get to more complicated ones at some point. But if the Lagrangian can be separated into kinetic and potential terms. Now, kinetic terms mean terms which are quadratic in velocities. Velocities mean time derivatives. Not space derivatives, but time derivatives. If the Lagrangian has a term which is a time derivative squared, or a time derivative of one thing times a time derivative of another thing, in other words, it's quadratic in time derivatives, then those terms are called kinetic. Right? So, for example, in our example, the term 1/2 phi dot squared is called kinetic field energy, kinetic energy of the field. It's not kinetic energy in the sense of something moving down the corridor here. It's kinetic energy in the sense that the field is moving with respect to time. Field is changing with respect to time. So this is kinetic, T. Let's call it T for, or just K. Kinetic energy would be that. Things which do not depend at all on time derivatives are potential energy. All right, so what are the potential energy? We call it U. That will have 1/2, in our example over there, 1/2 the space derivatives plus 1/2 So these constitute potential energy. If you think about it for a minute, when we worked out the problem of the chain of springs, the space derivative terms came from the stretching of springs. The time derivative terms actually came from kinetic energy of the motion of the mass points connecting the springs. So in fact, these space derivatives really do correspond to something more like potential energy than kinetic energy, but they're potential energy which depend on neighboring points, on the field configuration at neighboring points. But they don't depend on velocities, only on gradients. We could call these gradients, spatial gradients. All right, what else did we have in the potential energy? In the potential energy, we also could have this mu phi squared term. So I think it was plus mu phi squared over 2. Then kinetic energy minus potential energy is the Lagrange density. Right? Actually, is this the kinetic energy? Not strictly speaking, the kinetic energy is the integral of this over space. It's the sum of all the kinetic energies of all the fields at all the positions in space. In the case of a string, the full kinetic energy is the sum of the kinetic energies of all the moving mass points. So strictly speaking, the kinetic energy is the integral of this. Let me put it in blue here. It's really the integral d3x. And the potential energy would be the integral also. But sometimes we lapse into a simpler language and just call this term the kinetic energy without the integral, and this term the potential energy. Okay. And of course, we can have more complicated expressions. This does not exhaust all possibilities. In fact, there's no reason why you can't put here phi to the 4th or phi to the 10th power or whatever you like. But as long as it doesn't have time derivatives, it's part of the potential energy. Now, the Lagrangian is the difference of the two kinds of energy. Where did I put my... Yeah, I lost it. Lagrangian is the difference, but the energy itself, which in Hamiltonian mechanics becomes the Hamiltonian, of course, but let's not worry about that. The full energy is kinetic energy plus potential energy. So it's the sum of these. Phi dot squared plus the gradient of phi squared plus mu phi squared. Notice that in the energy in this form, all of the terms are positive. All the terms are positive, kinetic energy, potential energy, and even the term coming from the mu phi squared are all positive. Of course, there's nothing that prevents me from putting this in with a negative sign, but I didn't on purpose. So the energy typically has some kind of positivity associated with it. What if phi is absolutely 0? In other words, no field, no waves at all. Then the energy is 0. Phi is 0, the derivative of phi is 0, and so forth. The energy is completely 0. Also, mu phi squared is 0. And since the expression for the energy is positive, if phi is not 0, the energy of anything which is not just phi equals 0 is positive. So any wave or any configuration of the field is positive, has a positive energy, unless the field is just plain 0. Plain 0 is called a vacuum, and anything with a varying phi or a non-zero phi carries energy and is called an excited state. Okay, so that's energetics. And if you go back to the original formulation of mechanics, in the quarter on mechanics, you'll discover that there's a derivation of the fact that kinetic energy plus potential energy is conserved if the problem is time, translation, invariant. So this is our first conservation law, conservation of energy. Later on, if we explore more complicated Lagrangians, I'll remind you of a more general definition of the energy. But as long as the energy breaks up into a kinetic term, quadratic and time derivatives, and a potential energy term, then kinetic plus potential is conserved. That's a general theorem. We could prove it, but I didn't want to spend a lot of time at it since it really just follows exactly the pattern. It's not that I didn't want to do it. It's a little too intricate to go over again. Go back to your notes and as I said, it's a special case of mechanics. So you don't have to do it over again for field theory. It's just a special case of mechanics energy conservation. Now, there are other conservation laws. The other conservation laws follow from principles like this. let me remind you in ordinary mechanics. Supposing you have a Lagrangian, no, an ordinary Lagrangian, which depends on some q's and some q dots, not just one, but a whole family of them. Now, supposing the Lagrangian is unchanged if you make certain transformations on q, if you do something to q, and in particular, if you take each q sub I and add to it a small change which has the form f sub I of all the q's. This means some ith function of all the q's, including q sub I, q1 through qn. Supposing if I make such a change, supposing it's true that the Lagrangian just doesn't change, that's called a symmetry. Let me give you an example, or a couple of examples. Kinetic energy of a free particle, x dot squared over 2, mx dot squared over 2. Forget the integral. That's the Lagrangian. Is there a transformation that I can do that won't change the Lagrangian? Yes. Just take x and add a small displacement to it. This just corresponds to displacing your system a little bit. If you change x by a constant amount, incidentally, these q's here, these f's are not supposed to depend on time. No time dependence at all. Just a constant shift of some kind of the q's. Here's a constant shift of the x's. It just corresponds to displacing your system a little bit. If I shift x by a constant amount, it does not change x dot. It doesn't change the velocity. The change in the velocity is 0 because epsilon doesn't depend on time. So the Lagrangian doesn't change if you shift x a little bit. That's one example. Supposing I had added something. Supposing I had added, let's make it a harmonic oscillator, kx squared over 2. Now what happens if I shift x a little bit? This term doesn't change, but this term does change. This is just a statement that if I have a harmonic oscillator and I shift the coordinate a little bit, the potential energy changes. So the free particle has a symmetry, shift of x. The harmonic oscillator does not share that symmetry. But now let's take another problem. Let's take a problem with two particles connected by a spring. Let's call the position of the first one x and the position of the second one y. They don't correspond to two different axes. They just correspond to two particles, x and y. All right? What's the energy? Kinetic energy of the first particle is mx dot squared over 2. Second particle, let's call it capital M y dot squared over 2. Now, what about the potential energy? The potential energy only depends on the distance between x and y. All right? Depends on how much the spring is stretched. And so the potential energy, which goes into the Lagrangian with a minus sign, of course, that's going to have a spring constant, k over 2, and it's going to have x minus y squared. Okay? Now I assert that there's a symmetry. The symmetry is to add to x and y, each of them the same amount. X goes to x plus epsilon, and y goes to y plus epsilon. That's simply a shift of the whole thing. Both particles shifted by the same amount. What happens to the terms in the Lagrangian? First of all, what happens to x dot? X dot doesn't change. If you shift x by a constant amount, x dot doesn't change. No change in x dot, no change in the kinetic energy. Likewise for the y kinetic energy. X changes and y changes, but x minus y does not change. You've shifted x and y by exactly the same amount, so the separation between x and y has not changed. Potential energy has not changed. Again, we have a symmetry. It's the symmetry in this case of both particles being shifted. All right, so let's think of some other symmetries. Supposing I have some system of particles interacting with various kinds of forces and so forth. As I illustrated here, one symmetry is to shift the position of everything, shift in the x direction, shift in the y direction, shift in the z direction. As long as the forces are, as long as the potential energy only depends on differences, then again, this will be a symmetry. But we also have other symmetries, rotational symmetry. Supposing I rotate the coordinates, that's more complicated. In that case, more complicated formulas for rotating coordinates, but nevertheless, as long as the forces only depend on distances between particles, if you rotate a system, the energy doesn't change, neither the kinetic energy nor the potential energy. So again, another symmetry of the problem. Symmetries correspond to changes that you can make in the coordinates, time-independent changes that don't change the Lagrangian, that the Lagrangian doesn't vary when you make such a change. The value, the numerical value of the Lagrangian. Whenever you have a symmetry like that, you also have a conservation law. Let's prove that. It just follows very simply from Lagrange's equations, but we need a definition. Well, we don't need a definition, but we can use a definition. The definition of the canonical momentum conjugate to a coordinate q. All right. These are the q's and the p's. For every qi, there is also a conjugate momentum pi. Now, conjugate momenta may not look at all like what you're ordinarily accustomed to thinking of as momentum. It's a mathematical definition of something which, for certain situations, looks like ordinary momentum, but may or may not look and be familiar, have a familiar connection with mass times velocity. Angular momentum, for example, is a thing which doesn't look all that much like ordinary velocity. And there are lots and lots of other examples which look even less like ordinary velocities of things. But what is the definition of p sub I? P sub I is by definition the derivative of the Lagrangian with respect to q sub I dot. It's the thing in the left-hand side of Lagrange's equation. Lagrange's equation, or the Euler-Lagrange equation, can also be written in another form. They can be written in the form d by dt of p sub I, the time derivative of the ith canonical momentum, is equal to the derivative of Lagrangian with respect to q sub I. For each I. All right, everybody, this is review. I'm taking this to be review. The canonical momentum is dl by dq sub I dot. Incidentally, what is the canonical momentum conjugate to x? It's the derivative of the Lagrangian with respect to x dot. That's just mx dot, mv. So for this kind of Lagrangian, it is just your old familiar momentum. Okay? But more complicated situations, it may be something else. So this is its mathematical definition. D by dt, sorry, p sub I is the thing inside the square here. Okay, let's prove a theorem. Let's prove a theorem that if there is a symmetry, in other words, if when you do this operation, when you take each q and shift it by an amount f sub I, assume the Lagrangian doesn't change. In other words, assume that delta L is equal to 0 under such a transformation, under such a shift of the coordinates. All right? Then I assert that there is a symmetry. It is a symmetry. Then I assert that there's a conservation law. And it's very easy to work out. Let's see why that's so. Here's Lagrange's equations of motion. Let's multiply it by delta q. Well, Yeah. Let's take each one of these equations and multiply left-hand side and right-hand side by the change in Q when you do the little symmetry operation here. All right? Good. I could either write delta Q or I can write epsilon times F sub I of Q. This whole thing being delta Q sub I. Let's do it also here. You're not allowed to do something just on one side. We have to do it on both sides. F sub I of Q. Now, now let's sum. Now let's sum over all the i's. What's the left-hand side? The left-hand side is the derivative of the Lagrangian with respect to Q times delta Q. That's the amount the Lagrangian changes when you do this operation. But the assumption is that we have a symmetry. If we have a symmetry, then the right-hand side is by definition 0. The change in the Lagrangian when we shift Q times the amount we change Q under the symmetry operation. That's assumed to be 0. You don't prove that it's 0. For a specific Lagrangian, you prove that it's 0. But for a specific Lagrangian, let's suppose that the Lagrangian is invariant under that operation, then this side must be 0. Definition of a symmetry. On the other hand, the right-hand side here, these f's are supposed to be not time-dependent. These are constant time-independent shifts. Not a shift which depends on a time, but a shift which is completely independent of time. Then the time derivative of f is 0, and we can write that this is the sum of I d by dt of p sub I f sub I of q. In other words, you take the ith canonical momenta and multiply it by the amount that you shift the ith q. By this. That's equal to 0. That's what this says. Well, this is fantastic. That says we have a conservation law. The conservation law is the conservation of p sub I, f sub I of q. You take each shift, you take the shift of the ith coordinate, f sub I. I think I dropped epsilon out of this somewheres, but epsilon multiplied both sides. Yeah. It just went along with f. All right. We can drop it. If something is equal to 0, it's equal to 0 with or without the epsilon multiplying it. This quantity is conserved. Let's work out an example or two. Well, here's an example right here. First of all, delta x is equal to epsilon. Delta y is equal to epsilon. That's the common shift of both coordinates. All right? Well, that says that fx, that just says that fx is equal to 1 and fy is equal to 1. X just shifts by amount epsilon. The f is 0, is 1. All right? What about the canonical momentum? The canonical momentum conjugate to x, that's mx dot. The canonical momentum conjugate to y, that's py, is capital M y dot. What's the conserved quantity? The conserved quantity is the sum of p times the shift of each of the coordinates. The shift of each of the coordinates is just by 1 unit. I mean, you can drop the epsilon. The epsilon is just there to remind you that we're talking about a small shift. All right? So what's the conserved quantity? It's just px plus py, the total ordinary linear momentum. But it's only conserved because the potential energy doesn't change when you make a shift. Yeah.
So Px and Py aren't independently conserved?
No, they're not. No, certainly not. Just think about the motion of this two-particle system with a spring. The two particles are going like this. The x component of this momentum is not conserved. Yeah. It's basically the center of mass momentum which is conserved. Okay. If there was no spring, the two would be independently conserved. All right? Because of the spring, only one combination is conserved, and you find that combination by finding the symmetry. Okay. All right, let's apply this idea to classical field theory. Let's write down our Lagrangian and search for various symmetries. Yeah.
Was that Noether's theorem?
That's a simple case of Noether's theorem. Yeah. Yeah, that's exactly what it is. Noether's theorem is a little more general, but this is a simple case of it. All right, the first thing we have to do is we have to understand what we mean by coordinates and momenta, the conjugate momenta to the coordinates. In a field theory, the fields are the coordinates. They're not the coordinates x, y, and z. They're the analogs of mechanical degrees of freedom, the q's. So the coordinates are the fields, and they're indexed by x instead of being indexed by I. What corresponds to the canonical momentum? The canonical momentum over here is the derivative of the Lagrangian with respect to q sub I dot. Well, and we call that p, sometimes pi. I think I prefer to call it pi now. Pi sub I is equal to this. The reason I'm using pi is for whatever reason, it is conventional in field theory to call the canonical momenta pi's. I can't help the fact that, there are changes of convention as we go along. These were established long ago. But p and pi, same symbol. This is just a Greek p. So the canonical momentum, dl by dq dot, what does that become? It becomes the derivative of the Lagrange density with respect to phi dot. It's that thing that was somewheres in our, well, let's see, where is our Euler-Lagrange equation? Here it is. Well, one of these terms is d by dt of partial of L with respect to phi dot. All right. Partial of L with respect to phi dot is the canonical momentum conjugate to phi. It's usually called pi sub phi. And there's one at each point of space. At each point of space, there's a field phi, and at each point of space, there's the canonical conjugate to that, the canonical momentum conjugate to that field. So both sides are functions of position. What do we do instead of summing over I when we want to write some expression that in mechanics would be a sum over the coordinates? We integrate over x. We integrate over x. So phi is a function of x, pi is a function of x, and otherwise beyond that, it's just straight mechanics. Okay? Let's see if we can find some symmetries and conserved quantities associated with our simple field theories. We had some, let's take the simplest field theory that we've written down. Whew, I'm getting tired. I have a feeling I'm probably reaching your point of exhaustion as well as my own. Yeah? Yeah, you know. I think today's lecture was fairly heavy duty. Like, I'm not sure whether you've reached saturation. Somebody speak. Hmm? All right, I will go on a little bit, but I will review it next time. So you can tune out now if you like, and I'll try to, yeah. All right, let's take our favorite Lagrangians. Simple one. Phi dot squared minus derivative of phi with respect to x squared. And we could put y squared and z squared there too, but just leave it like this for the moment. Simple. I've set the speed of light equal to 1. Doesn't matter. Let's put the speed of light in. Can anybody spot asymmetry of this Lagrangian? Strictly speaking, the Lagrangian is the integral dx of this. Well, d3x. But this is the simple case for one-dimensional string. But I just don't feel like writing the remaining terms. So let's take this case, but there's no difference in the... Can you spot any symmetry? Translation of what? Which? There's translation of the x-axis, indeed, but that's, yes, we're going to do that one. There's a little simpler one. It's translation of phi. Supposing I take phi of x and everywhere's shift it by the same amount. Phi of x plus epsilon. This is a uniform shift of phi everywheres. Why is this a symmetry? Well, supposing I shift phi, what happens to phi dot? Nothing, because I'm assuming that epsilon here is constant. What happens to d phi by dx? Epsilon is a constant, remember, it's just a number. Nothing happens. So this Lagrangian doesn't change when you shift phi. That means that there must be a conserved quantity. What is that conserved quantity? It is, the sum over all, let's write the general formula and then make it specific. It's the sum over all the degrees of freedom of the canonical momentum times, times f sub I of q. But what is f sub I in this case? It's just 1, right? Everybody's been shifted by the same amount. So the corresponding f that would multiply here is just 1. F equals 1, everywheres. Everybody's been shifted by the same amount. And so the answer for the conserved quantity is the integral, sum becomes integral, dx, the canonical momentum conjugate to phi, times f, which is just 1. So it's just the integral of pi sub phi. But what is pi sub phi? It's the derivative of Lagrangian with respect to phi dot. So we've discovered a conservation law. The integral dx of phi dot of x is conserved. Now, what does that say? Well, it says what it says. That, for example, if you started the string, let's think of it as a string, and we start the string at time t equals 0 with some arbitrary shape and some arbitrary velocity moving in some way, so that at every point on the axis there is a phi dot, then the integral of phi dot won't change with time. What will happen? This phi dot, which is going up over here, might get pulled back down. We know the string wiggles. So this upward phi dot might get pulled back down, but at the same time this downward phi dot would get pulled back up, and the net integrated value of phi dot would not change with time. That's what we've proved. Okay, so that's a conservation law. Incidentally, it doesn't mean that the integral of phi dot is 0. It means the integral of phi dot doesn't change. For example, we could start out with the string absolutely stretched straight, but with some part of it between here and here moving upward, and every place else stationary. The integral of phi dot is positive. Why? Because phi dot is positive everywhere. It's not zero. And what will happen? With time, the integral, the field will move in various ways, but the integral of the velocity of the field will stay the same. So that's a conservation law, yeah.
If you have, but if the initial velocity is zero, but the string is stretched from its neutral position,
right?
What happens then? It looks like it's starting at zero velocity.
Yeah. The integral, oh, I know what you're worried about. You're worried about what happens if the string is pinned down at its ends? Yeah. Okay. The pinning down of the string breaks the symmetry. It breaks the symmetry. One way of thinking about the pinning down of the ends is to imagine that there's a huge force which is confining the ends of the string to stay at the same position. All right? In that case, the energy would change if you lifted the whole string up or down. So we're talking about translations of the phi coordinate. So it's the pinning down which breaks the symmetry of phi goes to phi plus a constant. If we were talking about an infinite string, we need to be talking, I should have said, we need to be talking about an infinite string which is not pinned down anywhere.
That Lagrangian doesn't apply to the finite string.
Well, there's something that breaks the symmetry for the finite string, namely the pinning down condition. There is another situation. Here, let me invent a different kind of string which really does have the symmetry. Let's imagine here we have a pole over here and a pole over here. There's a ring over here. There's a ring over here that can slide up and down the pole, and the string is stretched between these two. Okay? All right. Now you can shift the whole string without any cost in energy. You can't shift the whole string if the ends are pinned down. But if the ends are free to slide up and down, then there's a symmetry, which is the symmetry of translation of the whole string. Phi goes to phi plus a constant. In that circumstance, the integral of phi dot would be conserved. And you know what the integral of phi dot would be for this? Remember what phi is. It's just the vertical coordinate of the string. It would just be the whole ordinary momentum of the string moving up and down. So if you give the whole thing a push up, it'll just continue to go up. That's what it says. So you have to be careful and make sure that you really have the symmetry. And you would not have the symmetry if the ends of the string were pinned down, but you do have the symmetry if the ends of the string are free to move. Do you know the term Dirichlet and Neumann boundary conditions? Yeah, okay. So for Dirichlet boundary conditions, that means the string pinned down, you don't have the symmetry. For Neumann conditions, you do. All right, but this was just an example. And it's not a terribly interesting symmetry. In particular, if we had the term in the Lagrangian plus mu over 2, there should be a 1/2 multiplying this, mu phi squared minus mu phi squared, then we no longer have the symmetry because phi squared will not be invariant when you shift phi. If you shift phi, phi squared is not invariant. It changes. So if we have this mu phi squared term, we no longer have this symmetry. So this is not a very robust symmetry. It's just a particular case which was very easy to illustrate. Phi goes to phi plus a constant. And as I said, it corresponds to a sort of uniform center of mass motion of the whole string vertically along the phi axis. But an ordinary field in infinite space, an ordinary field phi in infinite space, if it doesn't have this mass term, where is it? If it doesn't have the term that I call the mass term here, then it will also have a similar symmetry. Phi goes to phi plus a constant. All right, next time, I think we're finished for today. Next time, we have to study spatial momentum, ordinary momentum. The stuff that when it hits you, knocks you on your, not field momentum, but the kind of momentum that really hits you when a high energy pulse of radiation hits you, it gives you a push, and that's a different kind of momentum than this field momentum.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.